In this video, I'm going to go through the steps of doing a bivariate regression to evaluate the relationship between self-reported height and actual height. And the data are based on a study by Stewart in 1987 that I've simulated to correspond very closely to the results reported by Stewart. And we'll find out if there's a relationship and how big the relationship is. And I'm also going to estimate what I would predict someone's actual height to be if they were 183 centimeters tall. So in order to conduct the analysis, I'm going to go through my trusted steps. Are the variables continuous? That's the first question I need to answer. Check that the variables are continuous. Well, height is a ratio scale. They are definitely continuous in nature. So that is an easy one. The second thing I need to do is look for normality and outliers. So I need to look at that through the Explore utility. I don't have to, but this is certainly an attractive way to do it. Statistics, outliers, and plots, and histogram, stem and leaf. Get rid of the stem and leaf. And we can see the skew and kurtosis levels are very low. So skew is 0.035 for self-reported height, and actual height is 0.026 for skew, well below 2.0, and they're very comparable in magnitude. Kurtosis is less than absolute value of 9. I feel very confident about this. Now, this study isn't about a test of the difference between means. I'm not looking to see that people self-report their height to be more than their actual height. That would be a separate analysis to look at that. In fact, it would be think about it. What do you think the answer to that would be? If I wanted to test whether the self-height mean of 177.65 versus the actual height mean of 175.51. It's numerically higher self-report, but I'm not interested in that. I would use a paired sample t-test for that, and I could test that for statistical significance, but I'm not doing that. What I want to do is determine what is the relationship between self-height and actual height, and build a regression equation with a bivariate regression. So the data are sufficiently normally distributed, and there are no outliers in the data set either, based on the interquartile range rule with a multiplier of 3. We can see that there are only some warning signals here. No asterisks, just circles, which are not quite outliers, based on the rule I described in the chapter Relevant Outliers. So now I can give myself a check mark for that one, and I can run the bivariate regression. I am going to want the confidence intervals, so I'm going to do it through normal distribution theory because the data are so normally distributed. So self goes into the independent variable because I'm using people's self-report scores as a predictor of their actual height. Is there a relationship? Who knows? Maybe the relationship is 0. I doubt it. It'll be positive, but we just don't know how big. And we'll click on statistics because we want the confidence intervals 95% through normal distribution theory. I could use bootstrapping, but I won't yet. I don't actually need it because the data are so normally distributed. So we can see here in this table that self-height is the independent variable, and we can see that the dependent variable is actual height. Dependent variable. And then we get the model summary, which really is more relevant to something called multiple regression, but you get it here in the bivariate regression case as well. And the model R is 0.96. This is essentially a Pearson correlation in the context of a bivariate regression. And then we get the R squared value, 0.922. So 92.2% of the variability in actual height is accounted for by self-report height. So there is a very large correlation between self-reported height and actual height. And the adjusted R squared is 0.922. There's no difference between adjusted and R squared because the sample size is so huge. Standard error of the estimate is 2.00. Most people don't report that. The ANOVA is irrelevant, really. We don't have to look at that in a bivariate regression. Then we have the coefficient table, which has a lot of important information. The unstandardized beta weight is negative 0.195. So that, I should say, that's the intercept, sorry. The intercept is negative 0.195. So if somebody self-reported their actual height to be 0, impossible of course, but technically if somebody did, we would predict their actual height to be negative. So I've mentioned in the textbook that the intercept can take impossible values. It's impossible to have negative height. But this is simply for the purposes of building a regression equation. We need the intercept. We need to start somewhere. Now, the unstandardized beta weight for height is 0.989, and it's statistically significant with a t-value of 133.71 and significance of p less than 0.05. In fact, it's p less than 0.001. And the 95% confidence intervals also support the idea that there is a statistically significant effect between self-height and actual height, self-reported height and actual height. And we can see that the lower bound 95% confidence interval is 0.975 and the upper bound is 1.00. So what does this mean? It means that for each centimeter, it's a unit increase. So this is measured in centimeters, self-height in centimeters and actual height in centimeters. And so this unstandardized beta weight says for each 1 centimeter increase in self-reported height, there is a 0.989 unit increase, like 98.9% of a centimeter increase in actual height. So people are exaggerating their height. For each centimeter, they're lying a little bit. And we can see that it's equal to a 1 unit increase in self-reported height is equal to 0.989 of a centimeter in actual height. And in standardized beta weight form, that is equal to 0.96. And that equals the R value, which is a Pearson R, in the context of a bivariate correlation. So the correlation is 0.96. It's a very large correlation. And the standardized beta weight can be interpreted by saying for a 1 standard deviation increase in self-reported height, there is a 96% of a standard deviation increase in actual height. So it's almost a 1-to-1. If we saw a 1.0 here, it would mean that there, for each 1 unit standard deviation increase in self-reported height, there's a full complementary 1 unit increase, standard deviation increase in actual height. That would imply a 1-to-1 relationship. But the relationship isn't 1-to-1. It's a little bit off. People are lying a little bit. They're exaggerating upwardly on average. And it's statistically significant. So give myself a check mark for checking those results out and looking at the intercept, the unstandardized beta weight, the standardized beta weight, and the 95% confidence intervals. I've done that already. Check. And they are consistent with the p-value. Now I need to check the scatter plot for linearity. And I'll go into Graphs, Legacy Dialogues, Scatter, and self-height on the x-axis and actual height on the y-axis. Click OK. And we're going to see, look at that. This is a very large sample size. Over 1,500 people in this actual study by Stewart. We can see a really nice positive slope in the relationship, and there's nothing nonlinear about this. It's just a straight line. Isn't that a nice looking scatter plot to see something like that? You don't see that very often in science, because usually what we're looking at are variables that are not obviously related. In this case, there's an obvious relationship between self-height and actual height, or self-reported height and actual height. I'm just going to manipulate things a little bit because I want to see where the intercept lands. I'm going to go to Scale, and I'm going to do that from 0 to 210. And I'm going to change this one as well, just to show you something. 0 to 200. Well, that actually should be 250, because that one is 250. Whoops. I'm going to get rid of... No, I actually could keep that. So that is what the scatter plot looks like when I put 0 as the scale. And I'm going to put an intercept in there, I should say. And we can see that it's almost through the origin. It's almost a 0, but it's not. If we actually looked at it more closely, we would see that the y is a little bit negative of 0. A little bit less. And that's what this is coming from here. So the intercept is negative 1.195, and we can see that in this large sample size, we can see that the intercept is almost going through 0. Yeah, anyway, so there is, I was going to get rid of the regression equation, but there you go. It still looks good, and we can see that it almost goes through 0, and this is a little bit less than 0. So that's what it's trying to tell you. It's a little bit less than 0. If we looked at it with a magnifying glass, we would see it, possibly. Okay, so I've looked at the scatter plot. I think the effect is linear. I feel comfortable with that. And check for the distribution of residuals. I really feel like that's probably going to be the case. So I'm going to save the standardized residuals just to look at the distribution, look for some outliers. So that's created a new variable in SPSS right here. And I'm going to analyze those residuals to see that they're normally distributed and there are no outliers. I really don't think there will be. So let's look at that. And look at that histogram, just really nicely normally distributed. And no outliers, nothing deviant, nothing really going on here, no asterisk values, and a nice normal distribution. So yeah, I feel confident about this, about just sticking with the results that I've got. So the last thing I'm going to do is I'm going to check homoscedasticity, and I'm going to do that by getting the absolute value here for the z-scores. I've discussed that earlier in the chapter, so I'm not going to cover everything here. This is just an exercise. The chapter does describe how to calculate a correlation between the predicted scores and the absolute residuals. And that's what I'm going to calculate here. Absolute, in parentheses, residual, click OK. So that's created a new variable that I'm going to correlate with, and then I'm going to get the predicted standardized scores. I don't need the standardized residuals, I just need these now. Click OK. And now I'm going to run a correlation between the absolute values, residuals, and the predicted values. And my hunch is the correlation will be very close to 0, because there is nothing going on here that is suggestive of homoscedasticity. In fact, look at that, 0.014. Now I could carry that analysis further if I wanted to with a co-anchor test, but you really could just stop there and say, look, there's no correlation. Whether you did it with Pearson or Spearman, I could correlate it with the Spearman as well. Nothing going on, no matter how I analyze it. And I'll lastly do the co-anchor test just for fun and really support my argument that these data are totally fine as they are. So the independent variable goes in the explanatory variable, the outcome variable in the actual height. Again, I assume you watched the video where I talk about heteroscedasticity in the foundation section of the chapter. And you can see that the p-value for co-anchor is p equal 0.560. That is not less than 0.050, and therefore I can assume that homoscedasticity is present in these data. So there's a very substantial relationship between self-height and actual height, and it's statistically significant, and the unstandardized beta weight is equal to 0.989. Now I said, let's calculate the value. If somebody said they were 183 centimeters tall, so if you met somebody and they said, I'm 183 centimeters tall, what would your best guess be about their actual height? Well, we can calculate that in SPSS a couple of ways, but we could actually just get SPSS to calculate regression and linear and save for us a variable that is a predicted value but unstandardized. So this is going to do the prediction equation for us. And because there are at least a couple of people in the sample that have a height of 183, we can actually look at what their, say this person's 183, that person's 183, and we would predict that they're really 181-ish, 181 centimeters tall, not 183 centimeters tall. And again, I could calculate that with the regression equation if I wanted. If I didn't want to use SPSS, I could calculate that with the regression equation. So it's really 183. I need to multiply the unstandardized beta weight by the x value, in this case here 183 times 0.989 equals 181.987, and then I need to add this negative value of 0.195. So plus negative 0.195, and I'm down to 181.79. So if I calculated that at this decimal place, at these decimal places, I would predict 181.79, which is very similar to what SPSS predicted it to be with the utility where I save it as a variable. The difference being simply due to rounding. I use 3 decimal places, and SPSS uses, 10 more, who knows, something large. So that is what you'd expect. You can shave off a couple of centimeters off someone's height if they tell you that they're 183 centimeters. On average, that would be your best bet, to shave off a couple of centimeters. So that is the answer to that question about the relationship between self-height and actual height. I will note that if somebody said they were 170 centimeters, you can't just shave off 2 centimeters. You have to apply the regression equation. It will be less than a 2 centimeter reduction. You'd have to calculate it. So that is all for me, and I'll hope you enjoyed this video and you actually learned something about regression.